Today we're going to discuss torque. What is torque? How do we measure it? How do we calculate it? And so on. But we've already done an activity, and for those of you who are watching this at home that weren't in class, just kind of follow along with the logic here. I'm going to kind of go over what we did in the activity. So here's what we did. We took a meter stick and we pinned it right here. So somebody was holding it right at the bottom, keeping it from sliding away. They used a little bolt through the hole in there. And then somebody took a spring scale and with a loop of yarn or a string around it and pulled it this way with 5 newtons of force. And we said, hey, on the meter stick, they did that at the 95 centimeter mark or 0.95 meters, and they pulled it this way. Okay, and then what we did, now if I'll let my pencil be the meter stick, if I hold it at the bottom, but then take a force and pull it to the left, of course it will want to rotate. And that's what torque is. Torque is, when a torque is applied to an object, it makes an object want to rotate rather than translate. If you apply a force to an object, a force makes the object translate. But a torque makes an object want to rotate. Now, of course, force is involved with torque, but there's something else involved. And so this is what we did. We applied a force, if we F2 at 80 centimeters or 0.8 meters to the right, we pulled this to the right, and we pulled, holding this to the left, and we measured the force. And then we slipped that down to what we called R3. R3 was equal to 0.6 meters, and we pulled it to the right with F3, and then we measured that, and then we slipped it down, and we pulled to the right with F4 at 0.4 meters, and then we tried F5, but this didn't work because the force that we had to apply to keep the stick straight up was greater than what we could measure with that spring scale. And so this is what one student got after doing the experiment. And we can see a pattern here. That this is F2, F3, F4, and then F5 was more than 20 newtons. So as to hold the stick straight up in equilibrium, the torque that was trying to make it go clockwise was had to be canceled out by a torque that was trying to make it go counterclockwise, and this is clockwise, right? So because the stick was being held fixed in place, and what wasn't, the stick was in equilibrium, and so there was no net torque on it. If there was a net torque on it, it would start to rotate, but we were holding it fixed. And so, and what we noticed is that as the location of our force moved closer and closer and closer to the axis of rotation, the force required to hold the stick straight up became greater and greater and greater. And then just for fun, we multiplied them together. And we said that, hey, what is 5 newtons times 0.95 meters? Well, it's 0.475. Now I'm going to put the units in here. And my handwriting's pretty good, Kendall. So, okay. So this is Newton meters. And here we got 0.8 times 6. That's 4.8 Newton meters. What's 0.6 times 9? I think this was a little bit higher than it should have been. Maybe it should have been like, 8 newtons instead of 9. How many of you got 8 newtons? Yeah, most of you got 8 newtons. So I'm going to say that this, if you measure carefully, it's probably about 8 newtons. I'm kind of fudging. It's not good to change your data. But they got 5.4 Newton meters. And this is 0.4 times 12 Newton meters. Now this is unknown because the force required to keep the stick was greater than 20 newtons, and that's greater than what we can measure with those spring scales. But notice that these numbers are all very, very much the same when you multiply them together, because that is torque. Torque is, the way we calculate torque, and you can come get your notebook, this is very good. Torque is equal to the lever arm times the force. Now I like to put it in R times F, and there's a reason for that that you'll get later on. But what is lever arm, and then this is force? This is how we define torque by definition. Okay, well, we're going to get a little fancier than this here in a minute. But torque is equal. Now we have a variable that we use for torque, and it's a tau. Tau? It's a Greek letter. It's a Greek letter, capital T. So just kind of make a cursive T, and that'll work. But what you do is you kind of make this little curve, and then a little curve like that. And that's a tau. And that's the variable name that we use for torque. And this is going to be, now lever arm, we're going to call it R. Now R is the distance from here up to where the force is applied. Okay, that's R. And then, of course, we use the letter F for force. Now, it makes sense to use the letter R for this. And because, look at this meter stick. If I apply this force and pinned it so that it rotates around the bottom of the stick, what's it going to do? Well, it's going to move in a circle with a radius of R. So we're going to use the letter R to represent that lever arm distance. And what is it? It's it's the distance from the axis of rotation to the application of the force. Am I on screen? Not quite. To the application of the force. It's really a position vector or displacement, but we'll call it a position because we're always going to make the axis of rotation our origin. So here's the origin, here's where the force was being applied, so we're going to go R times F, and that's going to define our torque. Okay? And so this is an equation. And notice, I can have positive torques or negative torques. Now I'm running out of time. I got about 5 minutes left, so I got to go quick. If you're trying to rotate in this direction, okay, now this is the opposite direction that a clock moves. So we call this counterclockwise. Oops, I'm off screen. Counterclockwise. Whereas these forces, when you moved it down, they were all trying to make it rotate, in this direction, which we call clockwise. Now, counterclockwise, if we're going to call that a positive torque. We're going to learn this thing called the right-hand rule later on. But if it's trying to curl this way, counterclockwise, by using my right hand and I curl around, look at the direction of my thumb, come straight up. We're going to call that a positive torque is counterclockwise, whereas a negative torque is down. So when we had like torque 1 plus torque 2, that equaled 0 because the stick wasn't being moved. Now, if we go R1 times F1 plus R2 times F2, that should be equal to 0. Okay, now let's figure out what F5 should be, because we couldn't measure it. But we know that torque 1 plus torque 5 equals 0, because the stick wouldn't move. Well, this is R1 F1 plus R2 F2 equals 0. So let's solve for F2. F2 is equal to negative R1 F1 over R2. Okay, now let's plug in our values. This is 0.95 meters. F1 was what? 5 newtons. And what was R2? Or I'm sorry, not R2. I meant 5. Gosh darn it. I'm trying to go too fast. The fifth one down. The one we couldn't measure. And then what was R5? Was 0.20 meters. Well, let's predict what this should be. So 0.95 times 5 divided by 0.2 equals, and you get 23.7 or about 24 newtons. Now, what about this negative? What does that negative mean? Well, it just means that F2 has to be in the opposite direction as F1. F1 was to the left, so F2 has to be to the right, or in the opposite direction. That's all that means. Last thing, and I've only got 2 minutes to do it, so I'm going to do this really slow. What happens if I have a stick like this? Let's take our meter stick, and we're going to pin it down, and here's how I draw a pin. I'm going to pin it right there. Oops, sorry. And I'm going to apply the force like this at an angle. So here's our force. Now, I'm just going to go through this real quick. Here's our axis of rotation. Here's where the force is applied. So here is our R. And we said that torque equals R times F. But there's a problem here. The force isn't perpendicular. The force is perpendicular, and it's got a component that's parallel. Watch. Here's this. I'm breaking the force up into its components now. I'm going to call this angle theta. Well, this right here, this is F cosine theta. And F cosine theta isn't trying to make the stick twist. It's not contributing to the rotation of this. Only the component of the force that is perpendicular to R contributes to the torque. So this is F sine theta. Now in our experiment over here, all the angles were 90 degrees, so we didn't need to worry about it. But here, this is the official definition of torque. So let me zoom all the way out so we can see the whole thing. Okay. And this is our new basic equation that we're going to use to calculate torques. If you add up all the torques and the object isn't spinning, then when you add up the torques, they have to equal 0. Anyway, that was kind of quick. Any questions? That is all.